Your AI app will get jailbroken. Maybe not today, maybe not through the first attack you test, but builders should design as if manipulation will eventually succeed. That isn't surrender. It's the starting point for a much more useful security question. If the model produces a compromised response, what can that response actually do? Can it read unrelated data, trigger a consequential tool, pass unchecked instructions into your backend, or will the rest of the system contain the failure? Serious defense starts when you stop expecting the prompt to be an impenetrable wall and start engineering the application for the possibility that someone will cross it. That changes the threat model. A manipulated answer with nowhere dangerous to go might be an ugly failure, but it's contained. Connect that same answer to broad data access and powerful tools, and now it can become an application failure. The model turn is just one component in the chain. The permissions, validators, confirmation gates, and monitoring around it determine the blast radius. So, here's the question that opens the loop. If the model can't be trusted to enforce every rule on every turn, what does the rest of the stack need to enforce independently? You'll hear terms like jailbreak and prompt injection used around this problem. The supplied findings don't provide an authoritative taxonomy, so we're not going to manufacture a hard distinction or pretend every team uses those labels the same way. For this defense playbook, the operational event is straightforward. Some input or context manipulates the model away from the behavior the builder intended. Once that happens, responsibility moves to the application boundaries around the model. The useful question for builders isn't which label wins. It's which trusted boundary the manipulated output reaches next. Conceptually, the dangerous path works like this. Content enters the application. The model interprets it and produces output. Then the application decides whether that output stays text or becomes authority. If it's passed into a backend function, used to select data, or translated into a tool call, the model has crossed from generating language into influencing execution. The defensive rule from the findings is direct. Treat model output as untrusted input and validate it before it reaches backend functions. The breach becomes consequential when untrusted output is quietly promoted into trusted action. And notice, none of this requires a working attack recipe. The model can be influenced by content, but the engineering failure happens at a boundary. Output becomes a function argument, a requested tool call, a data query, or an action. That gives defenders several places to step in without depending on the model to recognize its own manipulation. They can limit the available data, restrict which tools exist, inspect proposed arguments, pause risky calls, require confirmation, or independently block suspicious inputs and outputs. One model turn can be wrong, while the surrounding system still refuses to amplify it. So, what does it cost when manipulation lands? The verified findings don't document a specific incident, dollar figure, lawsuit, or company failure, so we shouldn't invent one. But they do support a concrete hierarchy of consequences. Risk goes up when a model can reach more data than its task requires, invoke high-risk tools without checks, take consequential actions without human confirmation, or send raw output into back-end functions without validation. Put simply, impact is shaped by capability and access. The more authority attached to a model turn, the larger the potential blast radius. Here's the turn in the story. You can't win the prompt war once and declare the system safe. Independent classifiers can block harmful content, but even their publisher recommends complementary defenses because universal jailbreak prevention isn't guaranteed. That tells us exactly what classifiers are and what they aren't. They're useful filters. They're not proof that every malicious input will be caught. A static launch time checklist has the same weakness. Adversarial techniques change, and systems run into failures their builders never anticipated. Defense has to stay active after launch. Now we can build the actual defense stack. Layer 1 is independent classification. An input classifier inspects content before it reaches the model. An output classifier inspects what comes back. Either one can block content that matches the harmful patterns it detects. But classifiers have a clear ceiling. They can't guarantee universal prevention. Think of them as independent checkpoints that reduce exposure, not as permission to weaken every layer behind them. Layer 2 is least privileged, the most direct blast radius control in the findings. Give an agent only the data required for its current task. Not every record the user could theoretically access. Not a broad pool of data, just because it's convenient. Only what's required right now. Containment is easier when unavailable information is genuinely unavailable to both the model and its tools. If a task needs one project, scope access to that project. The implementation may vary, but the architectural principle is precise. Minimize the data exposed to each operation. Layer 3 is risk-tiered tool permission. Not every tool call should face the same friction. Builders can classify tool permissions using concrete risk factors, let low-risk operations proceed, and pause high-risk calls for extra checks or human escalation. The important part is that this risk decision lives outside the model's persuasive text. The model can propose a call. The application assigns the tier and enforces the gate. That keeps generation separate from authorization. Layer 4 is the human confirmation boundary. Consequential actions should cross this boundary, even when the agent operates autonomously everywhere else. That doesn't mean someone has to approve every minor step. It means autonomy ends at a deliberately chosen point. The system shows the proposed action, the relevant details, and the moment of consequence. Then a human confirms or rejects it. If the model has been manipulated, this gate creates a chance to stop the action before it has an external effect. Layer 5 is backend validation. Treat model output the same way you treat any other untrusted input. Check the proposed function, its arguments, the target resource, and whether the operation fits the permissions already granted. The findings don't prescribe a specific schema or validation library, so that implementation is up to you. But the invariant stays the same. Fluent language doesn't bypass programmatic checks. A model saying an action is valid doesn't make it valid. The backend verifies the structure and authority for itself. Layer 6 is continuous monitoring. Monitoring is separate from input filtering, output filtering, permissions, and validation. It can block attacks, expose patterns that earlier controls missed, and change as adversarial techniques change. It also creates the feedback loop production systems need. Observe failures, find the boundary that failed or the one that was missing. Strengthen that layer. Then keep watching. Defenses should evolve from observed production failures, instead of staying frozen at whatever the team imagined before launch. Put all those layers together, and the architecture changes shape. Content is classified before the model. The model gets only task-scoped data. Its output is classified and treated as untrusted. Proposed backend calls are validated. Tool permissions are assigned by risk. High-risk or consequential actions pause for checks or human confirmation. Monitoring surrounds the workflow, feeding production lessons back into every control. No single layer promises to catch everything. The system works because when one layer misses, another independent boundary is still waiting. This is blast radius thinking. You're not claiming the model is immune to manipulation. You're deciding ahead of time how much damage a compromised turn can cause. Least privilege limits the data it can reach. Risk tiers limit the tools it can reach. Validation stops generated output from automatically becoming trusted code or arguments. Confirmation protects consequential actions. Classifiers reduce harmful traffic at both ends. And monitoring catches and teaches you about whatever the original design missed. The model stays probabilistic, but the authority around it becomes explicit, narrow, and enforceable. Here's the checklist you can apply this week. First, map every place where model output can influence a backend function or tool. Second, mark that output as untrusted and validate it before execution. Third, reduce each agent's data access to what its current task requires. Fourth, group tools into risk tiers and pause high-risk calls for checks or escalation. Fifth, put consequential actions behind explicit human confirmation. Sixth, add independent input and output classifiers where they can reduce exposure while keeping complementary defenses intact. Seventh, monitor production behavior and turn observed failures into updated controls. Do that, and Jailbreak resilience stops being one clever prompt. It becomes an engineering system. The real payoff is the shift in your mental model. Stop asking, can my prompt be broken? Design as if the answer will eventually be yes. Instead ask, what can an attacker actually do after manipulating the model? Which data becomes reachable? Which tool calls become possible? Which outputs get trusted without validation? Which actions happen without confirmation? Which failures would monitoring reveal, and how quickly could you update the defenses? Those questions lead to controls you can actually test. The objective isn't a perfect model turn. It's a system where an imperfect turn has limited authority. That's the builder's eye defense playbook. Assume manipulation can succeed, then make that success matter as little as possible. If you want neural stack to go deeper, the next breakdown could focus on one layer at a time, designing least privileged data access, building risk tiers for tools, validating model-generated function calls, or creating a production monitoring loop. Tell me which boundary is hardest in your application. And before you ship another agent with broad permissions, trace one compromised turn through the entire stack. You might not be able to guarantee the model never crosses a line, but you can decide what's waiting on the other side.